I'm excited to try a lesson that can actually have a double lesson in one class. So we're going to try and nail the language of x-intercept zeros and roots being related. When we talk about a graph, we talk about a graph that has x-intercepts. The x-intercepts of this graph are clearly at -2 and 3. I can read them off. When I look at a function and put it in factored form, I can set the factors equal to 0 and solve for zeros, and that's -2 and 3. And when I look at an equation which is equal to 0, I get to talk about the roots. And because this equation can be factored into two binomial factors, I recognize that those numbers are also -2 and 3. So the zeros of the function, the x-intercepts of the graph, and the roots of the corresponding equation are the same numbers. And today we're going to look at both the integral zero theorem and the theorem that allows us to talk about fractions. I'll go down to the cubic here. The zeros of the polynomial are 2, 1, and -1. And those zeros are actually all factors of the constant term. They're factors. And that's what we're going to focus on first, is factors of the constant term. Let's turn the page. So here is the theorem that we're working on. The zeros of an integral polynomial with a leading coefficient of 1 must be factors of the constant term. So when I look at the example presented, I get to list all the factors of 6, plus and minus. And those lead to potential factors of the polynomial. So all those potential zeros were written above. And if I turn them into potential factors, remember what that looks like. So turning them into factors just means write them in factored form, convert from zero form to factor form. We had two students who were trying to identify one of the actual factors of the polynomial. So they tried x minus 1 in the factor and remainder theorem, or tried synthetic division. And they found out that when they used x minus 1, they didn't get 0, so that meant it was not a factor. They tried x equals 1 as a factor, and they generated a 0. That means that x plus 1 is a factor, and then they were able to long divide. The same thing happened on the other side. They actually tried synthetic division of x plus 1, generated a remainder of 0, and now we've got the potential opportunity to complete factoring for this statement. So depending whose results you took, doesn't matter whether you worked with Luke or Nicole's work, the result of the division was the same. I generated a trinomial, x squared minus 1x minus 6, and I can factor that trinomial into x minus 3, x plus 2. And that's going to tend to be our habit, is we're going to try to find one factor using the factor and remainder theorem, and then apply synthetic division to find our polynomial in completely factored form. So talking myself through this one, list the potential zeros of this polynomial. Well, they're going to be the factors of 12. And the factors of 12 are plus and minus 1. Sorry, the factors of 12, plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 4, plus and minus 6, plus and minus 12. Now I'm looking to express the polynomial in factored form, and I'm going to show you a little trick of the trade. I'm going to plug into y1, I'm going to plug my polynomial into y1, and then I'm going to set my table value, my table set value to ask, and I'm going to see if I can find the factors of 12 more quickly. Let's see. So I have my equation entered into y equals. I've set my table set to start at 0, and I'm going to ask my table questions. So I'm going to ask it, what happens when x is 1? Well, when x is 1, y is 0. When x equals 1, y equals 0. So that means x minus 1 is a factor. Then I'm going to try minus 1. Minus 1 didn't work, so now I'm going to try 2. 2 worked. So when x equals 2, y equals 0. So x minus 2 is a factor. And then I keep going with negative 2. Negative 2 worked as well. That's awesome. X equals minus 2. That made y equals 0. So that means x plus 2 is a factor. Keep going. 3. 3 didn't work because it turned into 33. Negative 3. Negative 3 worked. X equals minus 3. That made y equals 0. So that means x plus 3 is a factor. I should expect that my fourth degree equation has 4 factors, or a maximum of 4 factors, and I found them all. I found them all by using the factor and remainder theorem from last class. So I can state the zeros. I have done that already. 1, 2, minus 2, and 3. And I've got my roots written out. X minus 1, x minus 2, x plus 2, x plus 3. Actually, those are my factors, aren't they? These are my factors. And the roots of the equation, possible solutions are 1, 2, minus 2, and 3. So maybe this is cheating, I don't know. But I know that some of you simply entered the equation and then took a look at your graph. And if you take a look at your graph, you can actually read the x-intercepts off of your graph. The x-intercepts are something your calculator will give you, and I can see that my graph crosses at 2 negative values, negative 2 and negative 3, and 1 and 2. So I'm able to read that off in a variety of ways. One more example. So you've seen the cheating way, or the shortcut way to finding the zeros. Now I'm going to try it in the method that we're supposed to, and that is by plugging in potential roots. Here I've identified that minus 1 is a root. I can synthetically divide minus 1 into my polynomial. So that's 1 minus 3 minus 3, 1. I've performed the synthetic division, and I've run into a trinomial that I cannot factor using factoring skills. Now I have to go back to that lovely quadratic formula. It is on your formula sheet. X equals b plus or minus the square root of b squared minus 4ac divided by 2a. So negative b plus or minus b squared minus 4ac divided by 2a. And hopefully you remember how the quadratic formula works. The b is my second value, or the value associated with x. So that's 4 plus or minus 4 squared, or negative 4 squared, which is 16, minus 4 times 1 times 1 over 2 times 1. And I've been asked to evaluate to the nearest hundredth, so we'll keep in decimal form. So 4 plus or minus 16 minus 4, which is 12 over 2. So just taking a bit of an opportunity to review radicals as well. I simplified my square root 12 into 4 times 3, and the square root of 4 comes outside, so that's 2 root 3. So then I can divide by 2 and simply have 2 plus or minus the root of 3. I'm not writing with my eraser. So we can evaluate that to the nearest hundredth, 3.73 or 0.27. Well, that's it for this lesson. We're going to take a quick look at lesson 6. So let's flip to lesson 6 as well. Thank you.